Started. We're talking about geometry of multiple images, and in particular epipolar geometry. So we've discussed three algorithms to compute the parameters of our matrix and our epipolar geometry, therefore, the fundamental matrix or the essential matrix. All algorithms work for either of those. Now remember, one of them is the 8-point algorithm, right? The first one that we defined. The second one is simple extension of the 8-point, but with n points, where now you actually use linear least squares to reduce or to minimize the error. And the other one was nonlinear least squares to compute those distances that we had defined that were squared with regard to our optimization parameter, and therefore we had to use nonlinear least squares. There is, however, a paper that I've posted in Carmen that argues that the advantage of nonlinear least squares over linear least squares is simply given by poor normalization of your variables, okay, of your entries. And it proposes a very simple solution to that. So let's look at this, because this is, if you are ever to implement an algorithm, that's the algorithm I would recommend that you use, or at least that you try first, okay? So the problem when we work in computers, obviously, is that there is only so much precision that you can have in your floating numbers, right, in your real domain. And that causes a lot of computational issues, but this can be easily solved by first normalizing your data points that we have in the image to have a zero mean and a small standard deviation. In that paper, the author suggests the square root of 2, but any number around this value would be okay. So what we're going to do, we're going to define a transformation, let's call it T, that transforms our points pi into pi tildes, okay? Such that our pi tildes are zero mean and have a square root of 2 for a standard deviation, okay? And the same is going to apply to the pi primes. I'm going to have a different transformation that gives me my pi primes tilde that are also zero mean and a square root of 2 for standard deviation, okay? And then with that, we can compute my new error function, which is going to be, as always, the sum from 1 through n of pi tilde transpose the fundamental matrix tilde pi prime tilde, and all this squared. Now note that I have added the tilde also to the fundamental matrix. Why? Because that fundamental matrix is defined in that new space after the transformation T and T prime have been applied. Once we find the fundamental matrix in that space, I need to transform it back into my original space, okay? So we'll do that. He also suggests that we can take advantage of the fact that the fundamental matrix has rank. Anyone remembers? What's the rank of the fundamental matrix? 2. Very good, right? The rank of the fundamental matrix is always 2, meaning that one of its eigenvalues is equal to 0, right? So we can take advantage of that And he suggests us using SVD to decompose the matrix and equal one of the singular values to 0. So this can be done by A. You compute the SVD of F tilde. So let's say F tilde now equals to U, S, and V transpose. Second, you define a new rank 2 matrix, let's call it F bar, which is equal to U, diagonal matrix of the singular values. So S is equal to a diagonal matrix of, let's say, R, S, and T. But now we're only going to keep R and S and make the last one equal to 0 and V transpose. And C, we are going to find define the final result, F. This is my F in the original space as my F bar that I have computed here transform back to the original space. So multiply by T on one side and T prime on the other. Okay. So let's review this quickly. Let me see if I can turn that on. Okay. Oh, there we go. So these are the slides that you have in Carmen. I also posted the slides in YouTube, in the videos in the description. So you can also find the PDF there if you're watching or rewatching the class. But basically, these are the drawings that you have in the slides that are the drawings I'm always referring to that you should have here in class to understand my attempts to draw these things on the blackboard. So we have two images, right, that we have called pi and pi prime. We have a three-dimensional point, capital P. That P is projected. Remember, this is the image in front of the pinhole, the normalized image, right, the virtual or normalized image in front of the pinhole. And that where that vector, O capital P, crosses pi, I have my image point. And when it crosses pi prime, I have my P prime point, right? And then all these points define this triangle. This triangle defines a plane, right? So they're all coplanar. All these vectors, O small p, O capital P, O prime, they're all coplanar vectors, right? And that's what allowed us to define our basic equation, P transpose F P prime equals 0, because that defines the cross product, right, and the inner product of these vectors in that space, right? So the cross product defines the normal vector of that plane, and the dot product is the dot product of two orthogonal vectors, therefore has to be equal to 0. Right? These are the epipoles. Remember, the epipoles are where this vector O prime crosses the plane pi, right? In some images, when you apply this in practice, you will see that your epipoles are outside your actual image. So it doesn't mean that they are outside the plane pi. They are not outside the plane pi. They are in pi. But of course, in reality, when you take a picture, right, there is a limited amount of information or visual field that you can see, right? And it can be that, depending on how you put your cameras, you're cutting where the pinhole, or the epipole rather, is. Okay? So the epipole is always on pi, even though it might not be in your visual image. If you extended the image to a larger size, then you'd always have it in there. And then we have the epipolar line, which connects these 2 points, P, E, and P prime, E prime. Okay? Now, what the epipolar line defines is that this capital P, as far as we know, if we only see small p, can be any of these points, right? So if we take a picture of that line, there'll be this line, and all these points would align on the line. So you have all the information that we've seen here in class. These are the derivations of the essential matrix that we saw in class. All the properties that we have defined. If you include now to the essential matrix the calibration camera or calibration model K of the fundamental matrix. This is the 8-point algorithm that we have defined. You have all the derivations here they have included, including this one right here. So this is the 8-point, and this one right here, which can be solved with linear least squares, right? This is the pseudocode or basic information for you to draw this on the images that you have. Now, you don't have to do that, but I suggest that you go home and practice with this. So remember that we have defined a line like always as, let's say, AU plus VV plus C equals 0, right? So the line would be A, B, and C, these three parameters, these coefficients, these three coefficients here that are given by the normal and the normal of the plane, or the line rather, and the offset, right? And then with that, you can plot this. This is a pseudocode that you need to plot the epipolar lines in your images. And in the calibration grid, for example, that you have in your project, right, you could plot the epipolar lines as well. You could have for every point correspondence here and here, right? So let's say this one and this one, right? So given that, I can plot this epipolar line, which is the line that corresponds to that point, and this epipolar line that corresponds to this point here. You see how this works? Okay. And as you can see, this is synthetic data with simulated cameras. And as you can see, the epipolar lines are almost perfect, but they're not totally perfect, right? Even in a simulation like this, they're not totally perfect, right? They're very close, but not perfect. They're not always at the center of the point, as we have seen here in class. This is on images, epipolar lines shown on these different images, so of the corresponding points. This is the derivations of the nonlinear solution that we have talked about. These are the typical methods that are used, these methods that we have defined here. And basically, it's just the amount of derivatives that you use and small changes from one to the other. I've added you a reference to a book that I think it's useful for that. This is a nonlinear equation that we work with. Okay. All right. Any questions? All right. Let's move on then. Very briefly, let me mention something very, very briefly. I'll talk about this later in the course, like much later, toward the end of the course. But I just want to say that this that we have seen here can be extended to as many cameras as you want. But it gets harder and harder as you add more cameras, right? With 2 cameras, it's really easy as we have seen here, with 3 cameras, which we will see later on. I'm just going to sketch some ideas now. With 3 cameras, it's quite doable. With 4 and more, it just becomes increasingly hard. Okay, it's still doable, but it becomes increasingly hard. Now, if you have the patience and the knowledge to do it, then you can get better and better and better at estimating the epipolar lines, epipolar geometry, and at solving the problem of that we're going to discuss next, which is to recover the z parameter of the points that you're observing, right? Because the points that you're observing are a projection of x, y, and z, so you only have 2 values, right, u and v. But in reality, you want to know x, y, and z. So that's our end goal. And the more cameras you use, the better it gets. So let me just sketch you the 3 camera case to give you an idea what this looks like. So imagine I have 3 cameras. This is my, okay, that's my 3rd camera, apparently. This is my 1st here, and I'm going to do my 2nd here. Okay, so this is my 1st camera. Let me call it pi 1. This is my 2nd, pi 2. And this is my 3rd, pi 3. Okay, so you have 3 cameras corresponding pinholes, O1 for the 1st camera, O2 for the 2nd, and O3 for the 3rd. So the way this should be is I have this image plane. This is my pi 3 right here, right? And the pinhole is behind this plane, right? So you are on this side, the world, and the pinhole is here behind. Okay? All right. So now if I have a 3-dimensional point, capital P, I have a 3-dimensional point, capital P, say right here. I'm going to project this onto the image. So the first image first. So something like this. Okay. Okay. I'm going to project this to the 2nd camera, so something like this, and the 3rd one. Okay, right? And then where it pinches the camera, here, this is my 1st point, small p1. This point right here, right? Where it pinches the 2nd camera, or it crosses the plane pi 2, it's going to be p2. And when it crosses the 3rd one, maybe here, it's going to be p3, right? So far, so good, everyone? Okay. Now it's when things get interesting. I have this vector O1 to O2, right? O1, O2 vector. Okay, let's draw this. This is the O1, O2 vector. And that crosses the plane pi 1 of the 1st camera and pi 2 here and here. And this corresponds to, what this called? Epipoles. Very good. I'm going to call this epipole. Well, let's leave it at this for now. Okay. Let's not complicate things yet. All right. But I have 2 more, right? Now I have O1 to O3. Let's see if I can do that. All right. More or less. And that's going to give me, say, this one here, which is, what's this called? This one when it crosses, again? The epipole, right? Okay. And here, it's going to have this epipole right here. And now I'm going to have this other one Whoa. Okay. There you go. And it's going to cross here, another epipole, and another epipole right here. Now let's name these epipoles. I'm going to call this one here, this epipole right here, E21, because it's the epipole of the second and first camera. And this one here, E31. This one here, I'm going to call it E12. And this here, E32. And these two, I'm going to call E13 and E23. Okay? Make sense? This is the one from 2 to 1. This is the one from 1 to 2. This is the one from 3 to 2, and so on, right? This one is 2 to 3, and so on. See how this works? Now let's draw the epipolar lines. Okay, so now we have the epipoles. We can draw the epipolar lines. Now for this point P1, I can draw this epipolar line that has to cross P1 and that epipole, right? That's by definition what we call the epipolar line. But note that there is another epipole, so I have another epipolar line, this one, right? And I could also connect these two epipoles, and I have a triangle here. This line here is called the trifocal line. And I can do the same thing here. I have these two epipolar lines and this trifocal line, and trifocal line here, and two epipolar lines. There you go. Okay, so far so good. It's just a lot of lines, but it's not complicated, right? Just a lot of lines and things to keep track of. Okay, now let's look at this. I'm going to start with the epipole E31, which is this one right here, okay? This epipole. Now, I'm going to define, well, I'm going to, hold on. I'm going to use 3,1 and 3,2, which is here and here. There are these two epipoles, right? Now, between these two epipoles, these 2 points, there is a matrix that connects them, right? That explains how to translate and rotate, the essential matrix. Now, of course, I'm going to have multiple essential matrices here, so I'm going to call this 1, 2. This is the essential matrix between camera 1 and camera 2. So now if I have E31 transpose essential matrix between 1 and 2 and E32, what should this be equal to? 0, right? Why? Anyone can tell me why this is 0? Because these two image points correspond to what? To the same three-dimensional point right here, right? You see that? Thus, E32 is the image of O3, isn't it? And E31 is the image of O3. So that defines this triangle, right? And therefore, this equation has to be equal to 0. You can come up with many equations like this here, right? There's not just one equation. There are, my goodness, a large number of equations that satisfy this. You can also define these epipolar lines with the essential matrix. So this epipolar line right here is going to be defined by my point, say P3, right? Times the essential matrix between 2 and 3, right? Which is the essential matrix that relates this camera with this one, correct? So if I know the point P3 in that image, right? Where was P3? Right here. Right? If I know this point P3, and I know the essential matrix between these two cameras, then I can draw this epipolar line. Right? So let's see if that's clear. What would be this epipolar line right here? Let's say that I want to draw this epipolar line with respect to P2, right? Then that would be P2 times what essential matrix? This one, right? 1, 2, and so on. OK, good. So we have this equation. I can draw two more basic equations here that are important. This is E12 and E13. Let's see where they are. E12 is right here, and E13 is right here. And these two are the image points of O1, right? And therefore, this is also equal to 0. And the same applies to E23 transpose, the essential matrix of 3, 1, and E21, that's also equal to 0. OK? And because that applies not only to the epipoles, but to the points, I can also write P1, the essential matrix from 1 to 2, P2. That's also 0, right? I have P2, the essential matrix from 2 to 3, P3, it's also 0. And P3, the essential matrix from 3 to 1, P1 is also 0, right? And it's easy to see that I'm going from 1 to 2, and that's what this essential matrix tells me, right? So this number has to coincide with this one and this one with this one, right? So now I have 3 times as many unknowns, but I have 3 times as many equations. So no problem, right? I can still solve this. There is an advantage when you work with 3 cameras versus 2 cameras. When you work with 2 cameras, you are restricted to this modeling, which is to use points, right? And point correspondences. But when you work with 3 cameras, you can actually work with lines, which is pretty cool. Now, lines define in homogeneous coordinates, right? So if I have the Li line, right, in one image, and I have a matrix that gives me the correspondence. So why don't I, OK, hold on. Let me do this first. So remember that we had Cp equals Mi capital P, right? Or as we've seen it before, P is equal to 1 over Z MIP, right? Same thing. Sure. OK. So Mi here is a 3 by 4 projection matrix, which means that I can define Li times MIP and equal this to 0, right? And that all it says is that now I'm considering a line that is also defined by this plane, right? And I can come up with equations like this and solve for lines rather than points. Now, of course, these lines, right, are given by my homogeneous coordinates, right, A, B, and C of a line, right? OK. Excellent. We'll see this later. As I said, almost at the end of the course. This gives you a set of equations, gives you the trifocal tensors. So we still have to talk about tensors and all this. We'll define all this terminology, don't panic. But this leads you to tensors, which is just an extension of vectors and matrices and scalars, right? So we'll talk about this later. All right, moving on. Any questions before I move on? All right. So what I want to talk about next is how to recover the coordinates of P, right? So remember, P is x, y, z, but my small p's are only u's and v's. And what I would like to do is to recover the three-dimensional structure of my world, right? So remember the classical application that we've been discussing. You work for an advertising company or some movie company, film industry, and you have a scene, right? And you want to add computer graphics in that scene. Now, the scene in the film is 2D, right? But the real scene is 3D. And unless you can interpret the 3D information of your scene, how are you going to add computer graphics in it, right? I mean, you have to. So there are two solutions. You either calibrate the camera is stationary, you calibrate the cameras and then you can solve it, or you can use multiple cameras, which is what we're doing here, right? Now with multiple cameras, when you use just two cameras, this is called stereo. Stereovision compared to the stereo that you may get in your sound system at home, right? Or in your earbuds, okay? But it just means that you have two cameras, obviously, two sensors. Same thing. So let's go back to our boring, by now hopefully, super boring drawing of two cameras, a three-dimensional point, capital P, O and O prime, P and P prime, okay? And I have E, E prime, and my epipolar lines. Excellent, right? We're very familiar with this by now. And now how can I use this to define or to recover my coordinates of x, y, and z for my point P? That's what I want to solve for now. Okay, so I'm going to write the equation of the epipolar line, which remember it's E transpose times P, or you could say F transpose P, I guess, same thing, either whichever you have. Right, so I have P, my point P here, and with that point P, I can compute L prime, my epipolar line here, right? And with my P prime, I can compute L here. But there's a problem with this, right? That I keep saying you have these point correspondences. But when you take two pictures of the same scene, who's going to tell you that this three-dimensional point corresponds to these point correspondences in the two images? Nobody's going to tell you that, right? Unless you have a genie in your box and in a box, and it can solve it for you. You have to find these point correspondences. How are you going to do that? Well, this is where the epipolar line comes in handy, right? So I start at this point P in my image, and I know, because of epipolar geometry, that my P prime can only be one of these pixels about this line, right? Only one of these pixels may correspond to my P. And how am I going to find it? What I'm going to do, I'm going to define a window around this point. So I have P, I compute L prime, and I'm going to define here a window, an area, right? A window of pixels, right? And I'm going to slide that window for every possible position about L prime, right? For all the possible pixels in L prime. And for every possible pixel, I'm going to obtain one of these, right? Let's call them Wi. Yep. For all Wi that are on L prime. Yes? OK. Now, at the same time, actually, let me call this Wi prime, or, well, Wi is fine. Let's leave it at that. At the same time, I'm going to take the same window here, centered at my point P, right? And let me call this one W bar, right? Now, the way you convert this window into a vector is straightforward. You take the first value of the pixel at the left top corner of your image, and you write it down as the first entry of your vector right here. Now you take the second pixel and you write it down as your second entry. And you take the third pixel and you write it as a third entry, and so on. Once you're done with the first row, you go back to the left pixel on the second row, right? And you write it down, and so on, until you finish the second row, then the third row, until you finish all of them, right? And that's your vector. And you do the same thing here, right? This is called vectorized. So you have vectorized. Usually this approach that we're using is scan the image or convert the matrix into a vector. And there's a function in MATLAB that does this for you, right? Very nice. OK, so now we have this in vectors. So now let's see what these vectors represent. Now these vectors, let's say that we only had 2 pixels in that image. Then this would be a 2-dimensional vector. And each of these vectors would represent to a vector, or let's define them as a point here in my space, right? And this dimension would correspond to the first entry of my vector, which tells me what is the luminance, right, of that pixel, right? And for the second entry, it would tell me what's the luminance for the second pixel, and so on. So that the space can represent, this 2-dimensional space can represent all the images of 2 pixels, all the images I can ever have, right? Now, what am I looking for? I'm looking for, right here, I'm looking for the 2 images that are as close to each other as possible, right? Now, because the orientation of these 2 cameras is likely different, and my light source may be here, this one may receive more intensity than this one, right? So the amount of luminance that I have in both entries might slightly differ, but the pattern should be the same, right? So what I'm going to do, I'm going to normalize these vectors to eliminate for this intensity change. And that I can do by dividing by their norm. And I'm going to subtract the mean to also make them invariant to translation. So I'm going to define my vector, or my distance, right? So if I want to compute the distance from each Wi to my W, I could just compute the Euclidean distance. That would be the Euclidean distance, right? But I'm going to divide this by their norm. Their norm times well, it should be squared, but all right, it's OK. I'll just write squared. Okay. Now what I'm doing here, I'm just computing the distance between W and W2 normalized. I'm assuming they're already mean normalized. Okay, so I have subtracted the mean. And what this does, this inner product, it's computing, if I normalize it like this, the cosine of that angle. So this is equal to the cosine of that angle, right? The inner product of two vectors that are non-normalized, it's nothing else than the cosine of that angle. And that's what I am going to use as my metric to determine which of the pixels in my line L prime corresponds to my pixel P. That's it. So I can automate this. It works really fast, right? It's 3 lines of code. Works super fast. And it gives me all the point correspondences for all the points in my image. Once I have this, now I am ready to use epipolar geometry to reconstruct the point. This is called reconstruction. So now I can reconstruct my 3-dimensional point P, X, Y, and Z. So to do that, I'm going to use the camera projection matrix. So let's call this the camera model of the first camera, the matrix M that projects from 3D to 2D. Let's call it M, right? And the matrix M that does a projection from P to P prime, let's call it M prime, right? So remember, these are the projection matrices that determine how I am going to go from X, Y, and Z to U, V, right? It includes the intrinsic and extrinsic parameters. Okay. So with this, I can solve the problem, which is the following. Let's see. This is what I have over there, right? If I have this vector U, actually, this is P, this is UV, and this is U prime V prime, then I can solve this easily, right? I mean, in closed form, because this point X, Y, and Z is the intersection of these 2 lines, right? So I can find the solution. But this is not what happens in practice. This is what's going to happen to me, because of that those matrices M and M prime. This is what I'm going to get. I'm going to have, whoa, okay. This is what's going to happen. I'm going to have my point P here, my point P prime, right? These are my O and O prime. And what's going to happen? That these 2 lines are not going to intersect, right? They're going to look like this in 3D space. One is coming from this camera, right? And it's going to look like this. And this other one is going to come from this other camera, right? So from this camera and from this camera. And oops, they don't intersect in 3-dimensional space. Why does this happen? Because these 2 matrices, M and M prime, are just estimates of what the real camera does, right? The real camera is not a pinhole perspective projection camera, right? Unfortunately. So these 2 vectors from O to P and O to P prime are going to be extended out, and they are never going to converge to a point, capital P. So there is going to be my point, capital P, somewhere here in the middle, right? So my point capital P will be here. You see what I'm doing? This is orthogonal to this and orthogonal to that, right? So there's these two vectors, right? Right here. And I can draw a line between them. And my point, three-dimensional point somewhere here in between, right? OK. So let's draw the equations for this, shall we? See what the equation should look like. If everything worked fine, this is what the equations would look like. I have P cross product MP. That is equal to 0, right? Right? Because MP right here, right, is nothing else than ZP, right? So if I have ZP cross product P, that has to be 0, right? OK. Now, P prime cross product M prime P, that also has to be equal to 0, right? All right. So this is what I should expect if they intersected. This would be 0. Let's write this in matrix form, because we always like to write things in matrix form. I can write this in matrix form as P sub x times M and Px prime times M prime times P equals 0, right? These are small p's in capital P. Now, this is the, remember, the skew-symmetric matrix of the vector P, right? Same trick that we did to convert a cross product into an inner product, right? And now I can call this matrix, I don't know, say U. So I have UP equals 0. Unfortunately, as I said, these two vectors don't intersect, so this is not equal to 0. It's equal to some number. But what do I want to do? I want to minimize that number, right? I want it to make this number as close to 0 as I can. Do I know of a technique that is going to give me that? What's that? Linear least squares. Yeah, you got it. So pretty easy, right? I want to minimize the least squares error, which is this one, right? Right? Excellent. So I can use linear least squares to find the solution for my point P, right? So I just find the eigenvectors and eigenvalues of my matrix U, right? Compute these eigenvectors and eigenvalues, and that's going to give me the eigenvector associated to the smallest eigenvalue, the solution for P, which is this P right here that I'm looking for. I'm done, right? All right. That's the beauty about linear least squares. You don't ever have to have a solution, but you can still find it. All right, any questions? No? OK. Good. So now that we know all the basics and we see how we can apply least squares and all the techniques and concepts that we have learned in the last several lectures, and if you have problems with these terms, please do go back and rewatch the videos. Please look at the slides. Please read the chapters in the book, because all these concepts are essential to understand everything else that we're going to do in the next several weeks. OK? But now we are ready to do very cool stuff. I mean, really nice stuff. OK? We're going to start with something that's called structure from motion. And that is how we're going to recover the structure of the object, right? The three-dimensional coordinates x, y, and z that I recover here, but not with two cameras, with just one camera. But what I'm going to have, I'm going to use time instead of a space, right? So stereo is a spatial algorithm because I have two cameras spatially distributed in two different locations, taking pictures at the same time. And structure from motion does the same thing, but with a single camera taking pictures across time. Okay? So let's see that. And we specifically in this class, we're going to talk about affine structure from motion and affine structure from motion for rigid objects. Now, I have to say that the most fun is the non-rigid structure from motion for perspective projection, and that I do cover in computer vision. So if you really like this, computer vision is just going to be even more awesome than this. But you'll see the great things that you can do with that. So I think that this is going to be now the first important topic that we're going to cover. It's going to be slightly more difficult than everything that we have seen. Not much more, but slightly more, just because when you work in the affine space, affine domain, things just look a little odd because, you know what, we do not live in the affine space. This is the Euclidean space that we are accustomed to. And that just makes things a little strange at first. All right. So this is called, again, affine structure from motion. You usually see it abbreviated as ASFM for affine structure from motion. Okay. So here's what we're going to do. We're going to take a three-dimensional object, right? And we're going to place it somewhere in a location. And I'm going to take a camera. I'm going to take a picture of that object. Then I'm going to move. And I'm going to take another picture. And then I'm going to move. I'm going to take another picture, and so on, right? That's one thing I could do. I could also have my camera right there fixed, right? And take my object and move my object. Okay? I can solve both problems. But this is a very hard problem. Let's see why this is hard. What's my goal here? Let's find a goal. Always helps to know what we want to achieve, right? Every time that you have to start a new project, let's find the goal formally first, right? As formally as we can. Okay, my goal is to recover the camera's position and the scene shape. This scene shape is what's called the structure. And this camera position is what's called the motion. Okay? Hence the name structure from motion. Because either the camera is moving or the object is moving, right? So to me, whether the coordinate system of the object is moving or the coordinate system of the camera is moving, it doesn't matter, right? The two coordinate systems are moving with respect to each other. And that's what I want to recover. I want to recover that motion, that camera position with respect to the object, and the scene structure. Okay, that is a lot. So let's make some assumptions, shall we? And these assumptions are meant to simplify the problem. We're going to assume for now on that point correspondences are given. Do you know how to find point correspondences? I gave you one algorithm. There are many others, but I gave you one algorithm. Okay? that you can use. So we'll call these always PIs and PI primes. I1 through n. And we're going to assume that the object is rigid. That means that the object cannot deform, right? So I can take this object and I can not deform the object and not break it apart, right? Okay. Let's put this into mathematical notation. I'm going to call my capital PJs my n three-dimensional points, so J 1 through n. And these are my three-dimensional points x, y, and z, or xj, yj, zj, right? And I'm going to write Pij, this is a small p, right? So this is the image, and this is the real world. So this is the 3D world point, and this is the 2D image point. Okay. Now, if this is the jth point, right, this specifies this j, the point, or the point number, if you will. And I specifies the camera now. Okay, or the camera number. And I'm going to assume that I have m cameras. So what's my goal? I want to recover the camera position. What does this mean? It means that I want to recover my MJs, right? Or MIs, excuse me. My MIs, right? I want to recover all my cameras. If I take M pictures, right, and the camera is moving or the object is moving, that means I have to recover M camera models. Right? And I want to recover the scene shape or the object shape, the structure, which is the capital PJs, right? That is a lot of information I need to recover. So assuming that the cameras can take any arbitrary form, I have how many parameters in my camera? So let's write this. Let's remember this is my equation, right? The image point is given by my camera, MI, and my PJ in homogeneous coordinates, right? Okay. And MI, it's given by my matrix A and my vector B, right? Remember that? And because this is an affine camera, right? We're talking about affine structure from motion right here, right? This is the affine camera model. And therefore, this has 8 unknowns, right? Okay. 8 unknowns. And P has how many unknowns? P? 3 unknowns, right? So in total, so my number of unknowns is 8m plus 3n. Phew, that's a lot of unknowns. All right, how many equations do I have? These are my equations right here. I get 2 equations for each camera and each point, right? Yes, so I have 2 times n times m, right? So number of equations is 2mn. Now, remember that we have talked before about homogeneous coordinates being defined up to a scale, right? But here, we're actually in the affine space, which means that we can only recover everything up to what's called an affine transformation. Okay? Let's see why. Let's see how this works. See this equation here? See this equation right here? Yeah? Okay, let me rewrite it over here on this side. How about if I write Pij, it's equal to, instead of mi, I'm going to say mi prime. And instead of pj, I'm going to say pj prime. Okay? Where mi prime, it's equal to mi, that matrix right here, right, times another matrix Q. With Q an affine transformation. Remember, an affine transformation is given by a matrix C, a vector D, a row vector of zeros, and a 1. And now Pj prime, I'm going to define it as Q inverse Pj. Okay? Now let's substitute mi prime and pj prime here. And if I do that, what do I get? I get mi prime q inverse pj1. And look at this. This cancels out. That's the identity matrix. So this is mi pj1. Whoops. My solution is defined up to an affine transformation, up to this affine transformation, right? So there is an arbitrary affine transformation that I can never recover. Okay? Remember, in homogeneous coordinates that I can multiply everything by a scalar on both sides, and I never recover that scalar, the true scalar. We have to assume, all right, my vector has norm 1 or has norm x. This is the same problem. That affine transformation is not possible to recover because any outcome that I get for m and p is going to be up to that q. Now, how many parameters do I have in that q? I have c, which is 9, right? Plus d, which is 3, so 12. So there are 12 parameters I can never recover. So I can write that my number of unknowns is 8m plus 3n minus 12. There are 12 I'm never going to be able to recover, no matter what. Okay? But this has to be smaller or equal than the number of equations. Otherwise, I cannot solve the system of equations, right? Otherwise, I'll have infinite number of solutions. Now, if it's equal, there's only one solution. If it's smaller, then there are no solutions, but I can use a technique that you, by now, may be familiar with, called linear least squares, to recover this, right? OK. So let's see. Is that possible? Does this ever hold? Let's see. How about if I have m equals to 2? M was the number of cameras. OK? And n, the number of points let's say I have point correspondences, I should say, to be precise. I have 4. So just 4 point correspondences, just 2 images. Can I solve it? Let's see. So let me run the numbers. So I have 2, where am I? Yeah, here. 2 times 2 times 4. And on the other side, I have 8 times 2 plus 3 times 4 minus 12. OK. So what is this equal to? This is 16. And this is 16. What do you know? They're equal. So if I have 2 cameras, I need at least 4 points. But if I have 4 or more point correspondences, I can solve for all my unknowns. So this problem is solvable with a relatively small number of images and point correspondences using linear least squares. And that's exactly what we're going to do. All right. To better understand this ambiguity here, which is going to be key, because let's face it, this is true, right? There's nothing we can do about this when we recover M and P with linear least squares. But I don't really want to have a solution up to an affine transformation, because as you're going to see, that's going to look really weird, right? But I need to understand what that affine transformation is to see what I can do to then recover the Euclidean solution from that, right? What's the Euclidean solution? Spoiler alert. What's the Euclidean solution? The Euclidean solution is when this C is equal to the rotation matrix, right? And this is the translation vector. So there will be a point at which we want this Q to actually define the Euclidean transformation. And the Euclidean transformation is a particular case of the affine transformation. Okay. All right. So let's define the basics of affine of the affine space or affine geometry to understand how we can do this. All right, this is affine geometry. All right. So affine geometry, in short, is the same as Euclidean geometry that we have already talked about, with the minor detail that we have eliminated our ability to measure. So we eliminate our ability to measure length, area, and angles. Okay. So in Euclidean geometry, it makes sense to compute angles like this, right? This is a right angle of these two lines, right? In affine geometry, it's not possible. It doesn't exist, okay? That measure doesn't exist. The length, we can measure in Euclidean geometry what's the length of this line. In affine geometry, that doesn't make any sense. The area of this a rectangle right here. I can compute it in Euclidean geometry. In affine geometry, that doesn't have any meaning, doesn't make sense. So what's left? Well, two parallel lines. If I have two parallel lines in Euclidean geometry, they are still parallel in the affine geometry. Good. This is good news, right? There is something that is still maintained. Okay. And although we cannot measure distances, angles, and areas, the ratios of distances, the ratios of angles, and the ratios of areas are preserved. Okay. So those I can use, ratios of distances or lengths, angles, and areas. Now you're going to think that what we're going to derive now, or want to describe now, in the affine space is really strange. But in computer vision, we're going to go one step further. We're going to go to the projective space, right? P. As a projective space, you're going to see it in a P like this of whatever dimensionality. In the projective space, you lose even that ability to measure the ratios of angles, the ratios of lengths, the ratios of areas. Parallel lines are no longer necessarily parallel. Almost everything is gone by then. One thing that the projective space must preserve is the concept of straight lines. So if I have a straight line, you see this line right here is straight line. There's nothing I can do that will bend it. I can never bend this line. It will always be straight in the projective space. There are things like this that are preserved in the projective space, but very few. Okay? Now, the projective space is a more generic thing I can define. The affine space or affine geometry is a particular case of the projective space, and the Euclidean space is a particular case of the affine, right? So it gets more refined as we go. It's more specific. All right, so let's draw this. Let's draw what we just said. So imagine that I have this space. Okay? So this is a space I have. And in that space, I have three collinear points. Let's call them A, B, and C. Okay? You see that? Have a space. Let me probably make this a little larger. Huh? I have three collinear points, A, B, and C. Okay? And now what I'm going to do, I'm going to apply an affine transformation to that space. Okay? Let's call this psi. And let's say that after this affine transformation, I end up down here in a space that looks like this. And my projection is going to end up giving me, so this is projected here, here, and here. So I'm going to end up with these 3 points. Let's call them a small A, B, and C. Okay? Now, if I compute the distance from A to B, right? My distance from A to B, let's call it AB bar. Okay? That distance is not the same as the distance from small a to small b. They're not the same. Okay? So these are, I mean, they could be the same, but generally they're not going to be the same, right? They're not necessarily the same. But if I compute the ratio of AB and say BC, right? So the distance between A and B, the distance between B and C, and I compute the ratio of these two, this is equal to the ratio of these other two distances. Make sense? And the reason for that is that that transformation transforms this distance from this into something shorter, but equally transform this into something equally short. Right? So the ratio of these two things is multiplied by the same scalar, and therefore dividing by them eliminates that scalar. Right? The same apply to angles. And if I had, let me repeat this here. If I had these two spaces that one is a projection of the other, an affine projection, and I had two parallel lines here. You see these two lines are parallel. Once I project these parallel lines onto this new space, they're still going to be parallel. There's nothing I can do to not make them parallel. Right? It is also true that the center of mass of a set of points also projects onto the center of mass, projects onto the center of mass of the points in the affine space, or the points after the affine transformation, because they're both affine spaces. Oh. Okay. All right. It's about time. It's actually the time. I'm going to give you the more formal definition of affine space in our next lecture, and then we're going to use that to recover the three-dimensional structure and the motion of the camera using linear least squares. All right. See you next time.